In this video, we are going to do problem solving related to our chemical bonding models from Chapter 9. Always keeping in mind our periodic table. This is helping us to understand what sorts of bonding will be involved, whether it's metallic, ionic, covalent. So we should keep this kind of ever present. Now we'll start off with ionic compounds. Those are the first ones we looked at. And this is the Born-Haber cycle that we put up. You should spend some time and make sure you understand what this cycle is telling you and understand how this cycle works. We're going to use this approach to calculate a lattice energy for a compound given enthalpy of formation, sublimation energy, bond energy, electron affinity, and ionization energy. In this case, let's calculate the lattice energy for cesium fluoride based on the following data. We have the bond energy of fluorine, the ionization energy of cesium, the electron affinity of fluorine, sublimation energy for lithium, and the enthalpy of formation for cesium fluoride. So you're going to want to write out all the reactions that are associated with these energetic values, and then you're going to do a Hess's law approach, just like we talked about in our first video for Chapter 9. And we're going to add up reactions such that they cancel to produce something that looks like the overall reaction for the lattice energy, which is cesium fluoride solid going to cesium ion gas plus fluoride ion gas. And in this case, the enthalpy of reaction for this process is the lattice energy for cesium fluoride. So take a moment and get some scratch paper and see if you can add the reactions for the above energetics together in a manner that will provide you with the lattice energy listed below. So this is what you should end up with. The first reaction is the enthalpy of formation. We have cesium fluoride solid going to elemental cesium and half a mole of elemental fluorine. And that puts the cesium fluoride solid on the reactant side, which is what we're going to need. And then the cesium solid going to cesium gas, sublimation energy, that cancels the cesium solids. The half a mole of fluorine going to 1 mole of fluorine atoms, that cancels the half mole of molecular fluorine on the first reaction. Then the cesium gas going to cesium ion, and then the fluorine gas going to the fluoride ion will get us everything that we need. Everything cancels to provide the reaction as below. And so we handle each of these using the proper Hess's law approach. We have to take minus on the enthalpy of formation for cesium fluoride, and we have to take 1/2 of the bond energy. And then the other values are added directly as they are. If we do this, we end up with the following equation. The lattice energy will equal minus the enthalpy of formation, plus the sublimation energy, plus half the bond energy, plus the ionization energy, plus the electron affinity. And if we plug all those numbers in, these pop out to give us a value of 758.5 kilojoules per mole. That's the measured lattice energy for cesium fluoride. There have been theoretical models that have been developed over the years before we were able to get all the data necessary. And there are theoretical models to predict lattice energies, but they fall short of the calculated values based on Hess's law. And so these are the preferable ways to do this now. We have our periodic trends in lattice energy, and we understand that as the charge goes up, the lattice energy goes up, and as the size of the ion gets smaller, the lattice energy goes up. So based on those trends, Order the following ionic compounds in order of increasing lattice energy: magnesium oxide, magnesium chloride, magnesium iodide, and sodium chloride. Take a moment to do this. Recognizing that lattice energy increases with increasing ion charge and with decreasing ion radius. So the lowest charge for these systems are the sodium, the chlorine, and the iodine. And the largest size are the iodine and the chlorine. So that leads us to know the lower end of this scale, which is sodium iodide. Next is sodium chloride. And after that, we pick up the higher charged species, the magnesium iodide, followed by magnesium chloride. And the highest lattice energy then corresponds to the magnesium oxide, the two smallest ions that also have the highest charge. This is the ordering of lattice energy from lowest lattice energy at sodium iodide to largest lattice energy at magnesium oxide. Here's our covalent bond formation potential well we've talked about. We know what the bond energy, that corresponds to the depth of the well, and the bond length corresponds to the minimum along the x-axis. And we can use bond energies to calculate delta H of reaction. We take the sum of the bond energies that are broken, subtract off the sum of the bond energies that are formed, and that gives us our overall delta H for reaction. So we have an equation for this. The heat released or absorbed during a chemical change is due to the difference between the bond energies of the reactants and the products. So this is the equation we'll use for our next problem. So this is a real problem here. This is a problem that where we can calculate the correct value for the standard reaction enthalpy. So we're looking at the reaction between C2H6, which is ethane, plus chlorine, going to C2H5Cl, which is ethyl chloride, plus HCl, hydrogen chloride. So we'll base this on the following measured bond energy values. The bond energy for chlorine is 243.4. The bond energy for the first carbon-hydrogen bond in ethane is 410.5 kilojoules per mole. The bond energy for hydrogen to chlorine is 432 kilojoules per mole, and the bond energy for C2H5, the ethyl moiety, to chlorine is 341.4 kilojoules per mole. Take a moment and plug those numbers in and see what value you get out. So we use this reaction, this equation for our reaction. And so we end up with a value of minus 119.5 kilojoules per mole. This is an exothermic reaction, giving off a significant amount of heat. Next, we have our Pauling electronegativity scale, and we should have that available. You should print out this figure here to have available to you when you're solving problems related to electronegativities. And here we have our cutoffs. Our 1.7 delta electronegativity is the boundary between ionic and covalent systems, and 0.4 is for the polar covalent versus nonpolar covalent systems. Classify the following chemical bonds as ionic, polar covalent, mostly covalent, or nonpolar covalent based on electronegativity differences of the elements constituting the bond. First, the carbon-to-carbon bond, the electronegativity difference is 0. That is a nonpolar covalent interaction. For carbon-chlorine, we take 3.0 minus 2.5 to get 0.5 as the electronegativity difference. This indicates this is a polar covalent bond. Magnesium to carbon, that's in magnesium carbide. Electronegativity difference is 1.3. This is also a polar covalent bond. Finally, magnesium bonded to chlorine, as in magnesium chloride. We have an electronegativity difference of 1.8. It's important to note that magnesium chloride, as you know, would have a formula of MgCl2. When we're calculating the polarity of the bond, we don't worry about the stoichiometry. We only care about the two constituent atoms in that bond. So you never multiply the electronegativity by a stoichiometric coefficient like 2 or 3 or something. You just take the raw values and subtract them. Next, we discussed the electron C model to describe the bonding and metallic structures. And to remind ourselves, we have metal atoms that take their valence electrons and put them into a delocalized electron C, where we have the metal ion nuclei laying in that C and held together by the electrostatic interaction. And we looked very early on at the transition between covalent, ionic, and metallic bonding. This is a worthwhile figure to look at to review how the transition occurs between these systems. Next, then, let's classify the bonding of the following materials as either ionic, covalent, or metallic, simply based on their positions in the periodic table. We have carbon tetrafluoride, magnesium aluminum, which is an alloy, C2H6, which is ethane, C3P2, calcium phosphide, and then MgF2, magnesium fluoride. CF4 involves two nonmetals, therefore we have a covalent compound. And the electronegativity difference is consistent with that. More importantly, the properties of this material are consistent with that. Next up, magnesium aluminum. The bonding here is metallic. Magnesium aluminum is an important, useful alloy. It's light and strong. Next, we have ethane involving carbon and hydrogen, both nonmetals, therefore the bonding is going to be covalent. Our next system is calcium phosphide. We have a metal and a nonmetal, therefore we have ionic bonding. And finally, magnesium fluoride, a metal plus a nonmetal with ionic bonding. That concludes Chapter 9.